is the kinetic energy at the initial state xi, and kf be the kinetic energy of the object at final state xf. The velocity acquired by the object when it reaches the point B is v after the displacement of s. The force that depends only on the initial and final position of the object. It is independent of the path taken. So the work done here is due to the conservative force. Hello everyone, welcome back to my session 3 on chapter 6, Work, Energy and Power. I am Nishman Anjama, Faculty of Physics in Vidhyaashram Pre-University College, the Temple of Excellence, Mysuru. So in the previous session, we discussed work-energy theorem for a constant force. We got to know that the magnitude of a force is constant. So in this session, we will study the work done by a variable force and derive the expression for conservation of mechanical energy. Let us try to understand what is conservation of energy means, what is the principle of conservation of energy means, and also we'll derive the expression for work energy theorem by a variable force. The previous session we have derived the work energy theorem for a constant force. If you have not watched my previous session, please go through the derivation on constant force, then come into work done by a variable force. Let's begin the session by understanding what is variable force. What do you mean by variable force? So the magnitude of the force keeps changing. It is not constant. The magnitude of force keeps changing. So in this variable force, the force that we commonly come across, that we commonly encounter is variable force. Say suppose you have an object. You push or you pull the object. You push or pull the object from one position to another position. So there is some work that has been done on the object. I am applying force. So there is some work that I am doing. So I am performing. So when I apply force, what happens? The object moves from one position to another position. So there is displacement of the object. So I can say work has been done. So this force which I apply is not a constant force. It's a variable force. The force that we commonly come across is a variable force. Because when we apply force, that is variable force, the force of the object at each point in its path of motion from the initial to final position keeps varying. So the magnitude of force at each point of its motion keeps varying. So let us try to understand this work done by a variable force with the help of the force versus displacement graph. So you can see here, in the x-axis we have displacement. In the x-axis we have displacement of the body. In the y-axis we have force. In the y-axis we have force as a function of x. F of x means force is a function of position x. So you can see each position xi to xf. From the initial to final position, we can see the displacement is along x-axis and force as a function of position. As we apply force on the object, that is variable force on the object, at each point of its motion, the force is changing. The force as a function of position is given along y-axis. So in this graph, suppose consider I have an object at point A. Suppose consider I have an object at point A. Now what happens here is, I'll apply a variable force. Why am I applying a variable force? In order to move the object from position A to some position B. So that's why what I require, I need to apply some force, that is a variable force. So when I apply variable force, that the magnitude of force keeps on changing. So when I apply the force on object which is at point A, it starts to move. It is displaced from position A to position B. It starts to move forward with change in velocity. At each point of its motion of the object, there is a change of force because we are applying variable force. So when the object is displaced, you can see it is not a linear displacement. It is not a linear force. It is a variable force. You can see how the force is varying throughout when the object moves from A to B. This pink line here represents the variable force. This is a variable force. If you had applied constant force on the object, then you had to get a linear line. But in case of variable force, there is a change in the force of the object at each point of motion of the object. So you can see a pink line which is representing variable force that is acting on the object which is at point A. So when I apply force, there is a displacement of the object. So some work has been done. With respect to displacement, I can say some work has been done. So you can see the displacement from point A to point B, from the displacement that is given by x, the displacement from the initial position to final position is divided into many rectangles. It's divided into many rectangles. So the area under the variable force, area under the line that is represented by a pink color is divided into many rectangular strips. So each rectangular strip is equal to one displacement. So displacement from initial to final is divided into many rectangular strips, where this is the first displacement of the object on application of variable force. This is the second displacement. This is the third displacement of the object. So at each displacement, the force is varying. Suppose here the force is constant. Here the force is 5 Newton. Here the force is 7 Newton. So at each point of the motion of the object, the force is varying. So at first displacement, the force may be constant. When it comes to second displacement, when the object is moving, the force might be 5 Newton, then the force might increase, then force might again decrease. So there is variable force acting along the displacement of the object. So displacement is divided into many rectangular strips. You can see on this graph. I'll consider one such rectangular strip. One displacement of the object among these many rectangular strips. Say this is A, B, C, D. I'll consider a rectangular strip A, B, C, D. So there are many rectangular strips. So I'm considering one displacement of the object, that is A, B, C, D. Now what is the work done in order to displace the object? What is the work done in order to cause a displacement in the object? I know work done is equal to product of force and displacement. I am applying force, there is displacement in the object. I have considered one small displacement of the object, one small rectangular strip A, B, C, D. So you can see along the displacement, force BD is parallel to y-axis. So the force is given by BD. You can see displacement CD. So displacement is along the x-axis. CD is on the line x. So CD, displacement is given by CD. So BD, CD. So this is giving the area. This is giving the area of the rectangle. So this entire area is equal to work done. If I calculate the area of the strip, that will give me the work done. So I have work done is equal to force and displacement. So force, you can see the line BD is parallel to y-axis. The force is BD and displacement is along the x-axis. So CD is equal to the displacement. So the area of this rectangular strip BD and CD is giving me the work done on the object, W. To be more simple, from position C, the object is displaced to D. That means for a small change in displacement, that is delta x. So this is given as delta x. The force that is parallel to y-axis, BD is parallel to y-axis. Y-axis we have f of x. So if I substitute, I will get, what is BD? It is my f of x. And what is CD? From the point C, the object is displaced to D. So there is small change in displacement. Final minus initial. So final displacement minus initial displacement is giving change in displacement. So it is delta x. So W is giving f of x dot delta x. So this is the work done. This is the work done. So there are many such rectangular strip. You can consider any of the rectangular strip and you can find out what is the work done. So I have considered ABCD rectangle and I got to know work done is equal to f of x dot delta x. So there are many such rectangular strips in the graph. So if you remove all the rectangular strips, this is how the graphical representation looks like. So the area under the curve, gives you the work done. From the initial position of displacement till the final position of displacement, you had many rectangular strips. Displacement was divided into many rectangles. So if you remove all the rectangles, the total area under the curve gives you the what is the work done on the object that is causing the displacement of the object. So what happens here? So in order to know what is the total work done, I have to sum up each rectangular strip. I have to add each rectangular strips from the initial position to final position. So summing up, what I have to do? Summing up, summation. This is summation. Summation, displacement initial position to displacement final position, work done is equal to summation of displacement. You get it as f of x delta x. So work done is what? F of x delta x. So this is the work done for a small rectangular strip. So I have many such rectangular strips in the graphical representation. So if I want what is the total work done, I have to sum up all the rectangular strips. So I have used summation. Delta x is very, very small. Delta x is a small change in displacement. So delta x is very small. So delta x is equal to 0. Delta x is equal to 0. So if delta x is equal to 0, I can apply limits. So I can use limit. So that is equal to limit delta x tends to 0 because delta x is very small displacement. Summation xi xf f of x delta x, f of x delta x. So this is work done. If I have delta x, displacement is very small, I can have infinite number of rectangular strips. So the formula, so the equation goes to definite integral. The equation reduces to definite integral. So I have work done W is equal to integral initial position, displacement of initial position to displacement of object to final position, f of x delta x can also be written as dx, nothing but the change in displacement. Delta x can also be written as ds. So this is the work done. This is the work done to displace the object from initial position to final positions. So this is the total work done. The integral, we are integrating from the initial position to final position. So we are getting f of x dx. So this is the work done. So area under this curve, each rectangular strips, area under this curve is giving me what is the work done. In order to displace the object by applying a variable force from position A till position B. So displacement in the initial position till the displacement in the final position, we are integrating all the rectangular displacements. So the area under this is giving me total area is giving me what is the total work done, which has the equation W is equal to integrating from initial position to final position. So this is the limit xi to xf f of x dx. So this is about work done by a variable force. What I am doing here, I am applying a variable force. So what happens? When I apply variable force, the object which is at point A starts to move in the forward direction. So there is change in the force at each point of its displacement, at each point of its motion. So from A to B, this is the displacement from the xi initial to xf final. So the displacement is divided into many rectangular strips. So you can see the pink line here represents the variable forces acting on the object. So if I consider one such small rectangular displacement A, B, C, E, what is the work has been done in order to move the object? So the displacement of small rectangular strip. So I know work done is equal to f of x, small change in displacement dx, BD into CD. So then what I did, I have many such rectangular strip. You can consider any of the strip. So there are many such rectangular strip. If I remove all the rectangular strip, this is the graphical representation. So the area under this curve from initial to final is will give me what is the total work done. So total work done is equal to integral of limits from xi to xf f of x ds. So we are summing up all the rectangular strips so that we'll get what is the total work done in order to displace this object from xi to xf. So remember, this is the equation for work done by a variable force, which will be helpful for us in the upcoming derivations. W is equal to integral xi to xf f of x dx. Delta x can also be written as dx. It's nothing but change in displacement. So next we have work energy theorem for a variable force. In the previous session, we saw work energy theorem for a constant force. Now we are deriving the same work energy theorem by considering a variable force. Variable force means the magnitude is not constant. The magnitude of the force varies continuously. There is change in the magnitude of the force. So consider the similar explanation that we had in the previous session. You have an object. Consider you have an object at position A. Consider you have an object at position A which is initially at rest. So initial velocity is 0. You will apply a force. You will apply a variable force. So the object starts to move. The object has some mass m which starts to move in the forward direction. And it reaches the point B. It reaches the point B and it acquires velocity V after the displacement of S. After the body being displaced from A to B, the velocity acquired by the body is V. Since I am applying variable force, the magnitude of force is changing continuously in each point of motion of the object. So when object is moving, that means it's moving with change in velocity. So a moving object will possess kinetic energy. So the moving body will possess kinetic energy. So there is change in kinetic energy. We know kinetic energy Ke for a constant force. Kinetic energy for a constant force is half mv square. Since we are applying variable force, object is moving forward with a change in velocity. That means it possesses change in kinetic energy. The kinetic energy is changing at each point of motion of the object. So what is the time rate of change of kinetic energy? What is the rate at which kinetic energy is changing? So that is given by dk by dt. It is given by dk by dt. So you can see dk is the change in kinetic energy of a body for a small time interval dt. The time rate of kinetic energy is dk by dt is equal to d by dt. What is the value of k? We know kinetic energy is half mv square. We know kinetic energy is half mv square. So what is the work energy theorem states? What is the principle of work energy theorem? It is very important again, as I mentioned in the previous session. The change in kinetic energy of a body is equal to work done on it by a net force. Here the net force is nothing but the variable force. So the change in kinetic energy of a body is equal to work done on it by a variable force. I am applying a variable force. So the object is displaced from position A. So there is a velocity coming into picture. So the velocity acquired at the final state B is V after the displacement of object That is S after the displacement of S. So the change in velocity, it will possess the kinetic energy. So each point of motion of the object, there is change in kinetic energy that is given by delta K by delta T. Rate of change of kinetic energy for a small time interval dt is given by dk by dt. So you have d by dt of K is what? Half mv square. So we are performing a simple differentiation, a mathematical differentiation here. So half mv is constant, half m is constant. Take it out. Half is a numerical value, it's constant, and mass of the body is constant. So we have v square, d by dt of v square, d by dt of v square. Now, how do you differentiate d by dx of x to the power? We have a formula in the differentiation. So that is equal to nx to the power n minus 1. Similarly, if you have d by dx of x square, how will you differentiate it? It will be 2x. n minus 1, 2 minus 1 is 1. So d by dx x to the power 2 is nothing but 2x. Similarly, if you have d by dt of x square, then that will be equal to what? Then that will be equal to differentiation of that is 2x dx. Similarly, instead of dx square by dt, I have dv square by dt. So it will be 2v dv. So it is 2x dx by dt. So instead of d by dt of x square, I have d by dt of v square. So I have 2v dv by dt. This is how we perform a simple differentiation. So we have a differentiation formula, d by dx x to the power n is given as nx to the power n minus 1. So using this differentiation formula, we are differentiating this term here. So that will be equal to half m d by dt v square. So what it will be? It will be 2v dv by dt. 2v dv by dt. So 2 and 2 get cancelled here. 2 and 2 get cancelled. So what it will be? It will be mv dv by dt. mv dv by dt. So what is dv by dt here? Change in velocity by time. Change in velocity with respect to time. So dv by dt is nothing but a acceleration. So what happens here? So equation will be mva. So dk by dt. So dk by dt is equal to mva. So what is m and a? From Newton's second law of motion, we know ma is equal to f. From Newton's second law of motion, I know ma is equal to f. So on substitution, I'll get fv. So dk by dt is equal to fv. So what do you mean by velocity here? Velocity is change in position by time. So I can write velocity as change in position by time. So simplify that here. So you'll get dk by dt is equal to f dot. What is velocity? Change in position by time, that is displacement by time. So t get cancelled, you'll have dk is equal to f dot dx. So dk is equal to f dot dx. So you can see here, consider this as first equation. For a small change in kinetic energy, you have the small displacement given, that is dx. For a small change in kinetic energy, that is equal to small displacement dx. So I want to know what is the total change in kinetic energy for a displacement of the object from one point to another. I just know what is the small change in kinetic energy for a small displacement of the object. I want to know what is the total change in kinetic energy that is causing the displacement from A to B. I'll make some consideration. Ki is the kinetic energy at the initial state xi, and kf be the kinetic energy of the object at final state xf. So let us make some consideration. Let Ki be the kinetic energy at initial position at initial position xi and kf be the kinetic energy at final position xf. Now what will be the total change in kinetic energy? Then I will integrate the equation 1. I am summing up. So I'll get the total change in kinetic energy. So integrating equation 1, that is dk is equal to integration of f dot dx. So I'm integrating equation 1 to get what is the total change in kinetic energy. So what is the limit? Kinetic energy from initial point to kinetic energy final point, and displacement from initial point to displacement of object from final point. So these are the limits that I am considering. Kinetic energy at initial position and kinetic energy at final position. So on integrating, how will you integrate now? If you have integration of dx is x, integration of dy is y, similarly integration of dk is x is k. So taking the limit as it is, what is the integration here? It is f is a function of x. So f of x dx is nothing but work done w. F of x dot dx is nothing but your work done, that is equal to w. That is equal to w. So if I substitute the limit in place of k, I will get it as upper limit minus lower limit is equal to work done. Upper limit minus lower limit is equal to work done. I have k here. I am substituting limits in place of k. Upper limit minus lower limit is equal to work done, because f of x dx, f is a function of s. So f of x dx is nothing but integration xf. F of x dx is nothing but work done w. We have seen in the first slide that w is equal to xi to xf. F of x dx is nothing but work done. So kf minus ki is nothing but what? Change in kinetic energy. So delta ke is equal to w. Delta ke, kinetic energy, change in kinetic energy of the body, is equal to work done on it. Work done on it. So we proved the statement of the theorem, work energy theorem. What it states? Change in kinetic energy of a body is equal to work done on it by a net force. So net force here is nothing but a variable force. So if I consider an object which has mass m, which is moving with some velocity. So when I consider I have a body or an object of mass m which is initially at rest. So initial velocity u is equal to 0. So from A, I am applying a variable force, not a constant force, a variable force. So object starts to move in the forward direction. So there is change in velocity. The velocity acquired by the object when it reaches the point B is v, after the displacement of s. After the displacement of s. So I say there is displacement. So I say there is some work that has been done. So since I am applying variable force, there will be change in the each point of the motion of the body. There will be change in the kinetic energy at each point of motion of the body, because it's moving with some velocity. That means there is kinetic energy possessed by the object. Change in kinetic energy possessed by the object. What is the time rate of change of kinetic energy? So time rate of change of kinetic energy is given by dk by dt. I know what is k. What is kinetic energy for a constant force that we have derived? Expression for kinetic energy is half mv square. So half and m are constants. Take it out. So d by dt of v square. This is a simple differentiation now we have to perform. So we know in differentiation we have a formula d by dx x to the power n, that is differentiated as nx to the power of n minus 1. So using that I am differentiating d by dt v square as 2v dv by dt. You can see here Similarly, I am differentiating v square by dt, dv square by dt as 2v dv by dt. You will learn differentiation in your upcoming mathematics classes. So, this is the differentiation. 2 get cancels. So, here you can see after 2 and 2 get cancels, you have left with mv dv by dt. So, carefully look at mv dv by dt. So, what is dv by dt? It is nothing but acceleration, change in velocity by time. On substitution, I'll get dk by dt is equal to mva. So, what is m and a? From Newton's second law, it is force. So, F dot v. So, what is v here? F is force. What is v? It's velocity. Displacement by time. On substitution of displacement by time, I get dk by dt is equal to F dot dx. T get cancels, dk is equal to F dot dx. Consider this as your first equation. After you consider it as a first equation, now let us make a consideration that Ki, that is kinetic energy initially, be the kinetic energy at initial position xi, and Kf be the kinetic energy at final position kf. Then what happens? I will apply the total integral. I will take the total integral of equation 1 to find out total change in kinetic energy. So, what are the limits I have considered for integration? That is Ki to Kf, Xi to Xf. So, I have considered this as the limits. So, dk is equal to integration of F dot dx. So, after applying the integration of dx is x, dy is y. Similarly, integration of dk is k. So, applying limits, it will be upper limit minus lower limit is equal to integration of xi to xf. F of x dx is nothing but work done. So, change in kinetic energy, final kinetic energy minus initial kinetic energy is nothing but change in kinetic energy. Delta Ke, kinetic energy is equal to work done. So, we have proved the principle of work energy theorem using a variable force. So, it's simple differentiation and integration we have performed. Next, we have conservation of mechanical energy. So, what do you mean by conservation of energy? So, conservation of energy states that energy can neither be created nor be destroyed, but it can be transferred from one form to another form. That is the principle of law of conservation of energy. We'll study in detail the law of conservation of energy in our upcoming session. So, on that we have conservation of mechanical energy. Since we are studying about kinetic energy plus potential energy, that is my kinetic energy plus potential energy is nothing but the mechanical energy. I have to study the conservation of mechanical energy. For that conservation of mechanical energy, I need both kinetic energy as well as potential energy acting on the object. So, you can read here. You can read the statement of conservation of mechanical energy. What is the statement that states? Total mechanical energy. Total mechanical energy of a system is conserved if the force doing work on it, are conservative. So, the total mechanical energy of a given system is conserved if the force doing work on it, if the force that is acting on the object are conservative. So, the work is done by the conservative force. The work is done by the conservative force. We have studied in the previous session what is conservative force. The force that depends only on the initial and final position of the object. It is independent of the path taken. So, the work done here is due to the conservative force. So, the total mechanical energy of the system is conserved. That is both potential energy as well as kinetic energy of the system is conserved. Say for example, you are applying some force on an object to move it from one point to another. You are applying some force on the object in order to move it from one point to another. So, the work done there is a conservative force. The work done there is by the conservative force. So, when you apply the force, the work has been done. That means the total mechanical energy of that object is conserved, So, it is both kinetic energy of the object plus potential energy of the object. Sometimes kinetic energy can be more, potential energy may be less. Sometimes potential energy may be more, kinetic energy may be less. So the total sum of both kinetic and potential energy gives you total mechanical energy of the system. So that should be conserved. Consider I have the example of a ball. Consider I have the example of ball which is moving downward towards the ground where there is an influence of gravity. I am holding the ball in my hand. So there is a initial velocity, there is no speed. So initial velocity u is equal to 0. U is equal to 0. When I hold the ball in my hand, that means there is a energy stored in the ball which I am holding in my hand. So I have potential energy in the ball when it is at rest. So when I drop the ball down, when I leave the ball from my hand, what happens? The ball starts to move with some velocity v. The ball starts to move with some velocity v. So that the ball is in motion. That means kinetic energy is gained. Ball gains the kinetic energy and it reaches the ground where it has the influence of gravity. So initially when I hold the ball, it is at rest. So potential energy is there. So when I leave the ball, how it gains kinetic energy? Potential, it is at certain height h. As the height decreases, the potential energy decreases and it gives rise to kinetic energy. So ball gains kinetic energy and at height h is equal to 0, the ball reaches the ground with velocity v. So the total mechanical energy, that is both potential energy as well as kinetic energy, that is both potential energy plus kinetic energy is conserved. Potential energy might be more or kinetic energy might be more. The sum of potential plus kinetic energy of the system should be conserved. So there is a conservative force acting on the ball here. So gravitational force, what is pulling the ball down towards the ground? It is the Earth's gravity. Gravitational force is the one which is pulling the object towards the ground. So there is a conservative force acting on the ball, isn't it? Gravitational force is an example for conservative force. So gravitation is conserved. So the force that I have applied is nothing but the conservative force. So the total mechanical energy of the system is conserved. So let us derive this mathematically with the help of this diagram. So let us mathematically prove this statement. Consider a ball of mass m. Consider I have a ball of mass m dropped from a point A. So from a point A at a height h above the ground. So the ball is placed at a height h from the ground. You can see the ball is placed from height h from the ground. So let us divide this ball into 3 different positions. So initially ball is at position A, then we'll describe the position of the ball at B, then we'll describe the position of the ball at C. Say this is C. Consider the position of the ball at C. So I have 3 different positions of the ball now, at A, at B and at C. So I want to know what is the total mechanical energy of the ball at position A, at position B and at position C. So I have to derive this mathematically. So if I want to know total mechanical energy of the ball at A, at B and at C, to know the total mechanical energy, I need kinetic energy plus potential energy of the ball at A, kinetic energy plus potential energy of the ball at B, kinetic energy and potential energy of the ball at C. So consider at position A. Consider at position A. At position A, I want to know what is the total mechanical energy of the ball. Say the ball is lifted up. It is at certain height, that is h from the ground. So initially at position A, the initial velocity is 0. It is at A. Forget these 2 positions. I am just considering position of the ball at A. So the ball is placed at certain height h from the ground level. Just concentrate on this. So the ball has certain mass m and initially the velocity, it is at rest. It is in my hand. It is at rest. So initial velocity is 0. So what is the energy that a ball has? It is not moving. It is at rest. That is the potential energy. So at position A, the potential energy is given by formula mgh. So a ball has a potential energy mgh. So it is not moving. There is no motion of the ball. It is at rest. That means kinetic energy. The ball is not acquiring any velocity and it is not moving. So kinetic energy will be equal to 0. So what will be your total mechanical energy now? What is total mechanical energy? It will be kinetic energy plus potential energy. So that will be total mechanical energy, ME, mechanical energy is equal to kinetic energy plus potential energy. So total mechanical energy is equal to mgh. So consider this as your first equation. We got to know total mechanical energy at position A. It is mgh. It is mgh. Similarly, consider position of the ball at B. Now the ball initially was at rest U. Now what happens? The ball drops down. It starts to move towards the ground level due to the influence of gravity. When the ball starts to move, it is displaced from position A to position B. So it travels a distance x from A to B. Forget this. The ball has not reached the ground level. It has not reached the position C. So from A, it is moving towards B. So consider up to here. The ball initially was at rest. It is moving with some velocity now. That velocity, I'll take it as V. Consider this as V. Consider this as V. So it is, the velocity is V here. It is moving with some velocity V. So the distance traveled by ball from A to B be x. A to B be x. So now what is the position? So what is the height of the ball now? It will be h minus x. What is the remaining height? So forget this. Initially the position was at A. Initially the position was at A. At A I got to know what is the mechanical energy. Now ball has moved from A to B. Now from B it has to move to ground level now. For ground level now. So ball is at position B. From B to C, what is the left out height of the ball? It will be h minus x. So from A it has moved a distance x. So now at position B, I want to know what is the total mechanical energy. So what is the potential energy here? So there is no potential energy. Ball is moving. So what is the potential energy here? Ball is moving with some velocity and it is traveled the distance x. The remaining height is h minus x. So when potential energy is placed at certain height, now the height starts to decrease. The height is decreasing. So what will be your potential energy? The potential energy is decreasing. It is losing and it is giving rise to kinetic energy as height decreases. At this point, the potential energy will be mg h minus x. This is the height of the ball from B to C. It is h minus x. Now what is the kinetic energy? It is half mv square. It is half mv square. So I want to know what is v square. So I will use the third equation of motion, that is v square u square plus 2as. So v square is equal to u square plus 2. A can be replaced by g because it's a gravitational force which is pulling the ball down. So it is 2g. What is s? The distance travelled by the ball from A to B, it is x. So the distance is given by x. So what is the initial velocity? It is 0. It is 0. So v, initial velocity is 0 because the ball is moving with some velocity v. So v is equal to square root of 2gx. So substitute v in the place of half mv square. So you'll get kinetic energy of the ball at position B is equal to half mv square. So your square get cancels. So you'll get half m 2gx. So 2 and 2 get cancelled. So you'll have mgx as the kinetic energy. So I got to know what is kinetic energy. I have potential energy. So what is total mechanical energy? Total mechanical energy is equal to potential energy plus kinetic energy, isn't it? So substitute potential energy, that is equal to mg, height is h minus x, plus kinetic energy is mg. So you have mg h minus x, mg x, mg h minus mg x, minus mgx and plus mgx get cancels. So remaining is mgh. Total mechanical energy at position B is equal to mgh. So consider this as your equation 2. So the total mechanical energy at position B is also is equal to mgh. Now from the position B, the ball is moving towards the ground. The last position, that is the ground, that is position C, that is position C. So when the ball from the final position reaches the ground, so when height h is equal to 0, potential energy will be equal to 0 because it is not stored at certain height. So height is keep on decreasing. So when it reaches the ground level, h is equal to 0. So potential energy will be equal to 0. When the ball from A reaches the ground, forget this position now. When the ball reaches from position A to position C, the velocity will be v. The velocity will be v and h will be equal to 0. So at position C, what will be your potential energy? Height will be decreased. So potential energy will be lost. When height h is equal to 0, potential energy is lost and the ball has gained the kinetic energy, that is V. So potential energy is 0. What is kinetic energy? Ke is equal to half mv square. Isn't it? So what is V square? I will use the third equation of motion. V square u square plus 2as. So V square is equal to, ball doesn't have initial velocity. It is moving with some velocity. So this is 0 plus 2. It is A is replaced by G because ball is brought down by the gravitational acceleration due to gravity. So A is replaced by G and yes is replaced by height h. So what is the final height? From here to here, it was h. From the position A to position C, consider the ball has moved from here to here. What was the height? It was h. At the ground level, the height is 0. The height was h. So have V is equal to square root of 2gh. So it is 2gh. Substitute in kinetic energy. Ke is equal to half m root of 2gh whole square. Square and square get cancelled. So half m 2gh. 2 and 2 get cancelled. So remaining is mgh. So this is the kinetic energy. So what is the total mechanical energy? Total mechanical energy at position C. So that will be potential energy plus kinetic energy. Potential energy is 0 plus kinetic energy is mgh. So it will give you mgh. Total mechanical energy is equal to mg8 at position C. This is the third equation. So we can see the total mechanical energy is nothing but mgh at position C. At the 3 position of the ball, you can see total mechanical energy is same. So total mechanical energy of the system is conserved. So from equation 1, 2 and 3, total mechanical energy of the system is conserved because the force acting on the body is the gravitational force, that is nothing but the conservative forces acting on the body. The work is done by the conservative force. So both potential energy and kinetic energy is equal to the mechanical energy. So at each position, the total mechanical energy is conserved. So let us quickly sum up conservation of mechanical energy. I have a ball which is placed at certain height h, from the ground level to certain height h. So at position A, position B, position C, I want to find out the total mechanical energy, if it is conserved or not. If at the 3 points the total mechanical energy is conserved, that means total mechanical energy of the system is conserved. So I have divided the position of the ball into 3. Position A, position B, position C. First I will consider at position A. At position A, I want to know the total mechanical energy, that is nothing but potential energy of the ball as well as kinetic energy of the ball. When ball is at rest, the initial velocity u is equal to 0. That means the ball is placed at certain height from the ground. So the energy stored in the ball is the potential energy. The ball is not moving with some velocity. So kinetic energy is 0. Potential energy is given by mgh and kinetic energy is 0. Total mechanical energy is nothing but mgh at position A. Now what happens? The ball is moving from position A to B. Consider this part. Ball is moving from position A to B. What happens when it moves from A to B? What happens when it moves from A to B? It is displaced from position A to position B. It is traveling a distance. S is equal to x. S is equal to x. It is traveling a distance x. So when the ball moves from A to B, the velocity, the ball is moving means it is gaining kinetic energy. So velocity will be V. Consider velocity will be V. So at B, I want to find out what is the total mechanical energy. So potential energy will be, potential energy is not completely 0. It is moving with, ball is moving from position A to position B. That means height is decreasing. Potential energy is getting lost. It is getting converted into kinetic energy. Ball is gaining kinetic energy. So it is mj. What is height? mgh. What is h there? Height. So what will be the height here? It is h minus x is the remaining height. The ball has reached point B. Now what will be the remaining height? It is this height minus the distance travelled. So this will be the height. So half mv square is the kinetic energy. I don't know what is v square. I'll use the third equation of motion. V square is equal to u square plus 2as. So v square is equal to u square plus 2. A is replaced by g and s is the distance travelled by the ball. So it is x. So v is equal to root of 2g x. So substitute that in this equation. Square root get cancelled. Half and 2 get cancelled. So remaining will be mgx. Substitute this and this in equation PE plus KE. So you will get mgh. In the second equation also you can see the total mechanical energy when the ball reaches the point B is conserved. Now the ball will move from point B to C. This was A to B. Now the condition is the ball is moving from B to C. Ball is moving from B to C. So when ball moves from B to C, when it moving from B to C, the height is reduced. The height was h minus x and it was reduced. The height when it is moved from point B to C. It has moved from point B to C now. Forget this B. It has moved from point B to C. So from A, it has reached to C. From A, it has reached C. So what was the total height of the ball? It was h. Total height was h. From A, the height is getting reduced and at ground level, the ball is at ground level now. Height h is equal to 0. So potential energy is equal to 0. Now consider at position from A to C. From A to C, the potential energy is equal to 0. Ball has come to rest where the height is equal to 0. Kinetic energy, the ball has moved. So kinetic energy at ground level, it has kinetic energy. The velocity of the ball is reached ground is v. So half mv square, we use the third equation of motion and we have velocity is equal to 2gh. Here s is nothing but the height of the ball from A to C. So on substitution, I'll get mgh. Substitute Ke and value of Pe, total mechanical energy, I'll get it as mgh. So the total mechanical energy of the ball at position C is nothing but mgh. So you can see at 3 position of the ball, I had divided ball into 3 positions. With each position of the ball, the total mechanical energy is conserved. The total mechanical energy is conserved. So that is the principle stated by work energy theorem for a variable force. This is all about variable force. So that's all for today's session. In today's session, we studied work done by a variable force, that the magnitude is not constant. There is change in the magnitude of the force. Then we studied about the work done by variable force and we derived a small derivation for work energy theorem by a variable force. By a work energy theory of constant force, we got to know change in energy is equal to work done. Even here we proved in the work energy theorem of variable force, change in energy is equal to work done. But the force acting there was a constant force. In this work energy theorem, the force acting is a variable force. Next, we studied a conservation of mechanical energy. The total mechanical energy of the system is conserved and the force acting on it a conservative force. So, work done is by a conservative force because gravitational force which is pulling the ball is nothing but a conservative force. So, next I'll come up with more interesting session where we shall discuss the potential energy, principle of law of conservation of energy and the derivation on potential energy. And also we'll discuss more interesting topics in work energy power. Until then, take care, have a good day. Thank you.